This is kind of nanotechnology, isn't it?
Yes,
Yeah.
it is. Sort of the
Yeah.
other end of the spectrum. It is a giant
Yeah.
object that nanotechnology might make possible.
Okay, we are recording.
Okay, so Mark Haas spent several years working with nanotechnology while pursuing his PhD in chemical engineering at the University of Cincinnati. That research was largely focused on the synthesis and application of nanocarbon materials, especially characterizing their property. Since leaving the university in 2018, Mark has worked on metrology of nano and microscale technologies while working at Anton Par, a manufacturer of scientific instruments. So take it away. If you have anything to add, Mark, you can. Otherwise, just take it away.
That is a wonderful introduction. Thank you, Sue. The only thing I'd like to add is thank you all for having me back. Hopefully today will be as well received as the previous one. Now, if you'll excuse me, I'm going to try and share. I do have a few slides, but I don't seem to be able to share my screen. Does someone need to give me permission for that?
Steve, I tried. Do you have a
Who's-
button?
Who's the
Give me a
owner?
moment here. Let's see.
Yeah, it has to be the host,
The host can do it.
right?
But Steve is a co-host.
Spotlight. I don't under his
Wait,
name.
I got it.
All right.
On the button. All right, does that work?
It looks like it did.
Good.
All right, so you
There we
should all
go.
be seeing a bit of a PowerPoint presentation right now.
Yes.
Yeah.
Uh-huh.
So before we dive in, I want to talk a little bit about what I'm going to cover today, and then we'll go through the slides and open the floor up for discussion. So again, thank you all for having me back. Today I want to talk about the space elevator, a borderline sci-fi type idea, but sort of grows out of the nano talk we had last time, how very small things organized in the right way can have a very big impact. This is something that, while still not quite plausible, is potentially enabled by a lot of those small scale technologies working together to build one of the largest objects I could think of. So I thought the other end of the size spectrum might be worth investigating. As for the plan for the talk today, I want to cover a couple of things. First off, what exactly is this? I know not everybody is going to be following the crazy science ideas of the last 50 years very closely, so I want to cover a few of the basic properties of what this object is, how it works, and what sort of physics underpins it. We're then going to spend a little time exploring whether it's actually practical or not. Short answer, it's not practical, but it is plausible. And I think there's a lot to be learned by further investigating. So slight spoilers there. And then we're going to talk about why exactly we might want something like this, especially given some of the technical challenges it presents. And I hope to close up a little bit on why I think it's worth going out into the void, as it were. And then, as always, there will be plenty of time for discussion and questions at the end. This is something that I've talked about and kept an eye on for a number of years. So I've got lots and lots of little stories to share that don't quite fit into the formal presentation side of things.
Do you only want questions at the end, or do you take any questions?
I would prefer to do questions at the end, but I will have a few breaks along the way for addressing questions about topics I think are particularly important to understand.
Then you'll let us know. Thank you.
I will do so, yes.
And Mark, just
What?
I can't hear you. Steve, I can't hear
You're
you.
you're
Can't
muted.
hear you either.
He's actually not
testing 1, 2,
muted,
3.
but we don't,
Yeah.
yeah. Mhm.
Yeah, Steve, you're not muted, but we can't hear you.
Oh, what's
No,
going
we
on here,
can't.
guys?
No, we can't.
You got it. Whatever
And I
that
think
was.
it's not recording as well.
This says it's recording. I see the record icon on.
So do I.
Okay.
Okay, what did you do different? Just for Future.
Just for reference, all I did was I shared the entire desktop rather than the window, so that if I made a change in the screen, whatever was reflected on my desktop would show up.
Aha.
So I won't be able to see my notes, but that's okay. I can ad-lib a fair bit of this. So, all right. So I'm going to go over this again, if that's all right.
Sure.
Okay. So we're going to start off with a quick talk about what exactly is a space elevator, a little bit of its history, a little bit of the physics and theory that underpins it, and some of the practical designs that have sort of grown up over the years. I freely grant practical may be stretching the limits of the word, but that's kind of the fun of this kind of thing. Which is going to lead us into why would we want to do this and whether or not it's practical, implausible, pie in the sky based on unobtainium, whatever. And then just wrap it up a little bit with why I think it's worth going out. And as some of you may have noticed, there will be a few Star Trek references sprinkled throughout here, up to and including the name of my talk. So you probably guessed I'm a bit of a Star Trek fan. So this seemed like the perfect opportunity to slip some of that in. Let's start with an opening thought on this, because I freely admit that once I explain some of the idea here, it's going to seem a bit extreme and outlandish, and I'm not going to deny that, but I am going to lean on the words of one Arthur C. Clarke. You may have heard of him. Space elevator will be built about 50 years after everyone stops laughing. If I have a goal for today, it's to at least get everyone to stop laughing. You may not think it's practical. I'm 50-50 on that myself. But I do think there's some interesting technologies and some interesting parallel applications that make the whole thing worth investigating. Which brings us to what exactly is this? Now, most of what I'm going to refer to for this is basic design that's being promoted by the International Space Elevator Consortium. It's drawn from some work done by NASA about 20 years ago, as well as some ongoing work from JAXA, the Japanese Space Agency. So while it's certainly not a shovel-ready design, it's pretty close to what we think our first efforts at a space elevator might be. The main grain of salt with that is this is a preliminary engineering document. There are some things that are dictated by just the physics of the situation, but there are also a number of things that are design choices that have to meet some other parameter. I'm going to go a little light on some of the details of why those design choices were made, primarily because there are quite literally books covering these designs, and I know I can't fit an entire textbook into our talk. But if anyone has any specific questions about this that they would like to go into, I'm happy to cover it at the end. So to understand how this is supposed to work, we need to understand a little bit about orbit. So here's a rough top-down view of the Earth. We're looking at the North Pole. I'm somewhat optimistic about ice coverage, but that's a topic for another talk. And the Earth is rotating. Around the Earth, you can have a number of different objects in orbit. Depending on where your orbit is, those objects will have certain characteristics. So we've got this inner circle that's fairly close to the Earth. That's a good representation of what's usually called LEO, low Earth orbit. An object in this orbit has to have a fairly high tangential velocity in order to actually stay in orbit. The practical result of this is for every rotation of the Earth, something in low Earth orbit will go around the Earth many times. The space station, for example, goes around the Earth every 90 minutes to 2 hours. Space shuttle, back when that was still flying, same kind of thing. Low Earth orbit is actually very close by. The International Space Station is about 250 miles up, which means if it's flying overhead, I'm closer to those astronauts than I am to you. So LEO is not very far. But LEO is actually very difficult to get to, which is sort of where this whole idea starts to come in. We'll explore that in a little bit more detail later, but that's the short side of it. If you go way out from there to that outer red circle, generally speaking, we don't have too much in orbit out there, but the idea is once you get far enough out, the object is actually going around the Earth fewer times than the Earth would rotate in that period. Pretty much whenever we put something that far out, our goal is to get it on a trajectory to some other body rather than keeping it in orbit. But I like having that circle here because it helps us illustrate the important point, that green circle. That is geosynchronous orbit. An object in orbit there goes around the Earth once every 24 hours. Sort of the crossover point between going around the Earth faster than it spins and going around the Earth slower than it spins. What that means is an object in geosynchronous orbit above the equator is above the same point on the surface of the planet all the time. So let's switch to that reference frame. The Earth hasn't stopped spinning, the object hasn't stopped orbiting, but we've said these two are fixed with respect to each other. So let's slow the animation so that we can take a look at the system as a whole. Now this brings us to our next point. The key here, for the most part, when we talk about satellites, we tend to treat them as point masses. But realistically, the important thing is that the satellite's center of mass is at geosynchronous orbit for it to stay at that particular location above the surface of the Earth. I could have a slightly elongated satellite. In fact, this is quite common. But as long as the center of mass is maintained around that orbit that I'm interested in, the object stays in that orbit. And this is where we start to stretch things out, pun intended, into our space elevator. Let's take this to its logical extreme. I have a satellite that I am able to stretch out all the way down from geosynchronous to the surface of the Earth and send another section of it far out to balance that mass. Now, this would have to be small. If it's very heavy, we're going to have all sorts of problems because we're talking about cables and ribbons that are tens of thousands of kilometers in length. People do make things like that, but this would be fairly big, even for space. Now, there's some interesting consequences of this. Because this cable would be in orbit only at geosynchronous, if I'm lower down on the cable, I'm not actually in orbit. If I drop off, I'm going to fall. Similarly, if I'm above geosynchronous and I let go of the cable, not only am I not on orbit, I have an escape velocity. I can go to some other nearby body with the velocity that will be imparted. So let's talk some of the numbers, and this is where that ISEC design comes in. Some of these things are kind of required. The center of mass has to be at geosynchronous. The ribbon is going to be big. We say about 100,000 kilometers. That's going to be maybe a little longer, maybe a little shorter, depending on whether or not we use a counterweight and what we want to do with the upper reaches of this. You'll need a base station. We typically say in the Pacific, a few hundred miles west of South America. We say that largely because that location is very, very boring. There's not much shipping that goes through there. There's not much extreme weather that goes through there. So it's stable. And then the key to making this whole thing work is remotely powered cars that can travel up and down this cable. We call it a space elevator, but it's probably better to think of it as a space railroad. We have this large single piece of infrastructure, our track, going up and down that is maintained. And we have these transports that move up and down. And if they're not carrying their own fuel on board, they can do so in ways that are much more efficient than conventional rocketry, both in terms of money and in terms of total payload. That introduces some challenges itself, which I will talk about in a bit more detail later. We may or may not have a small station at geosynchronous orbit. You would need something there for the initial deployment and buildup of this type of tether. Similarly, we may or may not have that counterweight at the far end, depending on design. Well, that's the basic structure there. or at least as basic as something like this can be. Obviously, the ribbon itself is a limiting factor. Because this object is only in orbit at geosynchronous, it's actually in tension along its whole length, which means we need something with a fairly high tensile strength. We also need something with a fairly modest density because we have to get it up to orbit to start with. So the figure of merit we use is the specific strength, tensile strength over density. I'll talk about that too a bit more later. It doesn't have to be implausibly large, but it is among the strongest things we've ever made large. But what we find with this kind of conversion, most of the designs talk about having our remotely powered cars carrying about 20 tons of cargo. It's about 7 days for them to make their way from the surface of the Earth up to geosync. We can launch one of these every day or so. And on that basis, with some recovery of the crawlers, best estimate puts us down at about $200 per kilogram to get up to geosync. For reference, right now, you're looking at somewhere between $10,000 and $20,000 a kilogram to geosync, sometimes much higher. So order of magnitude shift downwards in cost. There's some assumptions there about what the cost of infrastructure like this would be. And as we all know from watching construction projects around our hometowns, infrastructure is always more expensive than you expect. But there's reason to think from some of these design and exploration studies that the cost would actually not be too difficult. We're looking at a few satellite launches to get everything up to orbit, one mission to deploy a very lightweight version of the tether, and then a series of missions to build that tether up to its final size and strength. Not cheap, but not outlandish either. Potentially same cost as the International Space Station, maybe even less. And operating costs are much, much lower. The other advantage with these crawlers is that since they move slowly, they don't need difficult to manage rocket fuels. They don't need very high-tech engineering to keep everything from shaking itself apart. We just need a car that can drive for 30,000 miles before it needs a tune-up. Not easy, but not impractical either. And the power beaming means that we can use power sources from the surface, beam that up to the crawler itself. Basically, that means we can use energy from the electric grid to make that happen. Rough calculations put the energy cost of driving that 20 tons up to geo at about $10 if we're looking at drawing the energy from the electric grid. So most of our operating cost would no longer be about hazardous fuels and engineering to survive the violence of launch. It would just be about the initial engineering and infrastructure emplacement. All right. Last thing I want to mention on this before we start looking at some of those points in greater detail, and before I open up for some questions about the idea itself. As I mentioned, we're only really in orbit at geosynchronous. The rest of the structure is balanced around that point by us shifting mass around. But because of that, if I'm lower on the tether, maybe I don't want to go to geosync. Maybe I want to put a satellite in low Earth orbit. So I can drop off early and then use a very, very small rocket to circularize my orbit below that. Right now, virtually everything that human beings do in space on an economic basis occurs in low Earth orbit. So this has that covered. Similarly, if I'm above that point, I fly off to somewhere else in space. Depending on the size, the length of the space elevator, you're usually talking about Jupiter as the limit. So probably inner solar system, Mars, Venus, asteroid belt, the moon, of course. But that covers a lot of the other scientific and commercial activity that we have in space. So this covers everything except deep space missions in terms of launch profile. And it lets us make the satellites themselves cheaper, as well as reducing launch costs once you have that initial capital investment, which, to be fair, would be non-negligible, as we'll see shortly. Before we go on, I realize at this point we are borderline sci-fi, so I figured this would be a good time to take any questions or comments about the physics here, and we can see if we can address those before moving on to the details. So any high-level questions?
Bernie's raising his hand.
How about a low-level question?
Ask away.
Well, I've been reading about space elevators for a while,
Mhm.
and the main problem that has been extolled is that the material science is not even close yet. In order to have a cable that will stretch the 24,000 miles that it needs to get to geosynchronous, it would have to be exponentially stronger than anything we've done, including carbon nanotubes. What's your feeling on that?
I actually have a whole slide devoted to that coming up. Short version, it's not going to be as easy as the initial Edwards designs were in the 90s and early aughts. A lot of that earlier work assumes that you would get the maximum strength, the maximum theoretical strength of a carbon nanotube material into your tether. That's not practical from an engineering perspective.
Mm-hmm.
But the best work we're seeing in the lab suggests that it would still be possible. And I'll talk now a little bit about what I mean by possible.
Mark.
With the Edwards design, if you have that maximum theoretical tensile strength, you can launch your space elevator on a single space launch system, and the cable weighs like 3 tons. Don't get me wrong, that'd be awesome. If somebody manages to make that work, more power to them. Realistically, though, we're looking at much lighter cables to start with and building it up to a final mass, probably around the order of 10,000 tons for the whole length. That assumes not the theoretical maximum for carbon nanotubes or other high-strength materials, but it does assume that the high strengths we've seen in the lab can be transferred to a final engineered object. I've got some numbers to go into that in a bit more detail later, but short version of my take is, yeah, the tether material is the limiting factor. Everything else is just engineering and politics. The tether does require a bit more fundamental science, but it's not outside of the realm of plausibility. It's within what we see in the lab in practical tests. We're just a long ways away from producing that at a practical engineering scale. It's a very good question, though.
Okay, according to the calculations I've done, the shuttle would have to be traveling at 145 miles an hour even to make it in 7 days. So that's another, I mean, you'd have to have living quarters on it if you're actually sending humans up in it.
Yeah, I will address that later. Humans are a whole other ball of wax. The first thing we'd start with, we'd just be looking at transporting satellites and hardware.
I see.
As much as I would like to make it easy for you and me to get up there, that's going to have to be a later iteration. The first iteration of something like this, people just require too much infrastructure to keep alive for that kind of trip.
Okay, that was all I had.
Okay, great questions, and definitely things to discuss in greater detail. They're key engineering considerations that every design of this object has to face.
There's a couple of things I'd like to ask. I mean, I'm sorry if I sound negative, but in this day and age, you have to look at the potential, dangers as well as the quite considerable benefits.
Of course.
I'm not sure I'm really up to speed on the mechanics of the system, but say you're extending the lower part down from geosynchronous orbit and you drop a wrench, so to speak.
Yes.
That wrench is going to come down with fearful kinetic energy.
Very much
And
so.
the thing that really concerns me is if by accident or malevolent intent, the damn thing gets severed right below geosynchronous orbit. The thing comes down as a coherent whole and it wraps around the Earth. So around the equator, I suppose, you have a region of non-significant, damage as this thing comes down with a fearful amount of kinetic energy. And it's a
Potentially, but not.
worldwide phenomenon, yeah.
Well, that's where this gets a little weird. That is very much a scenario that has to be considered. And anybody who's read Kim Stanley Robinson's Mars knows exactly how destructive that kind of event could be with that design. But let's take the case we're talking about here, where this tether weighs about 10,000 tons. That's spread across tens of thousands of kilometers. So as this comes down, it may initially start off with a fairly high velocity, but as it comes into the Earth's atmosphere, that's rapidly going to bleed away. This thing ends up with a density comparable to very lightweight paper or polymer films. Cleanup will be a mess, but as it falls through the atmosphere, it's going to come down like paper. So. Now, I still wouldn't want that to happen. That is very much a scenario we have to plan for, because nobody wants to drop confetti over the entire equator. That's an environmental catastrophe. But we're not talking about a rods from God type scenario here, where massive kinetic impactors annihilate everything along the equator.
That's good. I had not considered the fact that in your view that the cable is essentially not very massive. So yes, you don't want it to happen, but it's not, as huge a disaster as what might be with a massive cable.
Right. The key here is, even if it is a large object, it has a very, very high surface area in proportion to that mass. So
Right.
it just can't build up a very high terminal velocity once it gets to the atmosphere. For some tether materials as well, the amount of energy it's going to bring with once it gets to the atmosphere will just cause it to burn up rather than slow down.
Good point. Good point. One other, if I may, a quick follow-up. I sort of had a question like Bernie's. We are moving a car up and down this thing, or cars up and down this thing at something like 1,000 kilometers per hour. That does, we do have to get a substantial mass going at high velocity and keep it going that way
Oh, yes.
consistently. I think it's a non-trivial engineering challenge to have something going at what would be Mach 1 in an atmosphere, up and down this cable.
I will absolutely concede that point. My claim here is not that it would be easy, but that it lies within the realm of traditional engineering. It's something that could be done with what we already know.
Good. Thank you, Mark. I appreciate
You're
it.
very welcome.
Now, I have a few questions. First of all, I'd like to, first I've heard about this synchronous orbit. Was Bernie right? Is that about 24,000 miles out?
Yeah.
All right. Now, you said something that intrigues me. It has the property that if you leave it before, you head down, but if you leave it after, that is farther out, you head away. Is that
Yes.
correct?
That's correct.
So Earth's gravity stops having an effect?
Not at all. Where this gets a little weird to think about is every time when we're thinking about objects up in orbit currently, however distant that object is from the Earth, it has generally either established an orbit or is on a velocity towards a stable orbit. So the energy that the object has is either already stable at its orbit or on its way to a stable orbit.
Okay.
The challenge with this is that, or the advantage here is that since the cable itself is balanced at geosync, we've got that particular velocity for any object on it. That's not enough of a velocity to enter a high orbit if you drop below geosync, so you end up at a lower one. Above geosync, the velocity is greater than the velocity of an object on an orbit of that distance, and so celestial mechanics just takes it to the next stable energy position.
I think I understand. Okay.
Okay.
And my last question is, why is it limited to Jupiter? It seems to me it's boundless.
You actually could probably go further away. most of the designs typically limit it to the space elevator to a size of 100 to 120,000 kilometers, just to minimize the number of other space objects we would have to dodge. And at that distance, the velocity you end up imparting is roughly what you'd end up with needing to add to your spacecraft to get out to the orbit of Jupiter. If you had a longer cable, you could get further. That just introduces other challenges, so most designs cap it before that point.
Oh, so you were talking about length of cable, not potential to travel.
Right. The length of the cable above geosync is going to correspond to the type of velocity that can be imparted to a satellite, and thus what its delta V is to get to other objects in the solar system.
Okay,
For a 100,000 kilometer cable, that gives you a delta V about right to get out to the asteroid belt or maybe Jupiter. If you
okay.
made a longer cable, you could go further. There's just questions about whether the engineering trade-offs there would be worth it.
Got it.
Say, Mark, you said something that piqued my interest. It's real good that the cross section.
Who's speaking? Who's speaking?
I'm sorry, I'm Dave. Am I being nasty?
Only in that there are two other people with hands up.
Oh, I'm
Waiting
sorry.
their
I don't
turn.
see the hands. Where are they? My apologies. Please go
They're
ahead.
they're on the screen on, you put your hand up when to let people know you want to speak.
Okay, I'm quiet.
Steve M has his hand up and I have my hand up, so.
Okay.
So I guess I'll continue since I raised the ruckus. Two things. The first thing is I found very disappointing was your estimate that there was the potential of getting the cost down to $200 per kilogram.
Right.
Right now, NASA is estimating, or SpaceX is estimating, they're going to get considerably less expensive, down closer to more like $40 or $50 or even less per kilogram in 50 years or so. So aside from maybe a climate benefit, I'm not sure there's going to be much of an economic incentive on the Earth to create a space elevator. According to that, is that a problem?
I've got a couple of responses to that. Response number one, $200 a kilogram is my estimate, and I should say our estimate. The ISEC group as well ends up around there for an initial small volume space elevator like we're talking in this design. You can potentially get the cost much lower. I've seen it get as low as about $5 a kilogram.
Okay.
That does assume you have a larger cable built up. And our working idea here is that our first space elevator is meant to capture existing market growth within the space industry, which means primarily low Earth orbit satellites and providing design advantages there. You would then have secondary elevators built later as that market grows and as it adapts to having this kind of novel difference in technology to get there. And that would allow you to do larger payloads, human missions, scale up, essentially. So you could take advantage of those larger economies of scale to drop the cost.
All right, so that was an initial estimate, not a long-term.
Exactly.
mature technology.
That is not the ultimate limit of the technique. That's just what we think the first one would be like.
Okay. Second
The other
thing is-
one on that is I'm not entirely convinced by SpaceX's claims about cost per kilogram to orbit in the next 50 years. People have been working on dropping that cost per kilogram for, well, basically as long as space travel has been a thing. The best rockets we've got now maybe bring us down to $10,000 per kilogram, depending on whose numbers you trust. SpaceX has produced a rocket and a family of rockets that are no more efficient on a cost basis than any other rocket. So I'm going to be nice and say I believe their business plan is very optimistic and should generate a lot of interest, but that I don't think the engineering supports it. I'll talk about this a little bit more later when we.
This is also a NASA estimate. SpaceX is NASA. So,
Oh, I'm sorry, I was speaking over someone.
I'm sorry, I thought you were done. I just said, I saw a report that was a NASA report. And this is forward, just like the space elevator, these are forward-thinking kinds of estimates. 50 years is 50 years is a long time. So, I mean, that's,
It is.
Of course, there's speculation on both sides, no question about it. But but it seems like there could be, there still could be a learning curve and some serious competition there.
It's certainly possible. I don't want to rule it out completely. I like to think of myself as a good engineer, and I'm open to the fact that there are going to be design decisions and optimizations that I just haven't thought of yet that could enable something like that. But the number I always come back to for this is actually from Virgin Galactic. Early on, they were claiming that they were at $7,500 a kilogram for their early designs, and they expected that to get down below 1,000 by now. They've quietly retracted both of those numbers, and when you look at their books, it looks a lot more like they're currently at about $12,000 to $15,000 a kilogram. So even groups that think they have the technology and think they have the economics to make it happen still haven't really been able to crack that barrier. Now, again, there's a lot of engineering there. There's a lot of potential economies of scale if someone or some groups can figure things out. I grant this is a potentially competitive landscape over the next 50 years. I'm just not seeing rockets do everything we want them to when it comes to leaving the surface of the Earth.
The second comment was just that I have not read Robinson's books, but I mean, it's been clearly an idea in science fiction that while you can't necessarily do a space elevator on Earth, you could potentially do one on the moon or Mars. And so I don't know, I was hoping you'd be addressing that, whether the materials that we do have now, what would be their limitations? Is it possible to create a space elevator on a lower gravity system? Where's our limitation with current tech, where we see current technology, in other words?
Right.
Not
That
pushing the edge of our abilities.
Yeah, that is an excellent question, and I'm very glad you asked it. I wanted to bring this up at the tail end, but now is a very good time for it.
Okay.
You can build a space elevator on the moon using Kevlar, and it fits in a single high payload launch system. NASA and JAXA have both kicked around mission designs for that for the last 5 or 6 years. There's nothing on the books yet, but it is something that a number of groups are actively working on because it is absolutely within existing technology. The physics is a little bit different because of the mass of the moon and the way it orbits with respect to the Earth and that kind of thing. But ultimately, that tether is Kevlar, and not even expensive Kevlar. Just buy it off the shelf in kilometer-long rolls Kevlar.
Cool.
Yeah.
Okay.
So haven't done it yet, but the moon is absolutely something we could do now. It's just a matter of finding the money and time with the various space agencies.
Steve, did you have your hand up?
Yes, I do. Okay,
ahead.
so my original question, I was not calibrated to distances and speeds. I was going to ask, like, how does it climb the wire? Because I was imagining it having its own mechanical device, hand over hand going up the wire. But apparently, things are moving much, much faster than that. So is it rockets shooting it up? I'm guessing when it's going at a certain angular velocity at the lower elevations, it's going to be pulled to one side because it really wants to orbit more quickly. And as you go out past, it's going to be pulled to the other side. So I'm just curious how the car interacts with the cable as it's, I presume, rocketing its way up.
Excellent set of questions. It would not be rocketing its way up. We actually would be looking at having some sort of a mechanical contact between the vehicle itself and the cable. A tracked system, a set of wheels like you might see for newsprint or other paper processing, where that thin ribbon of material is drawn through a series of rollers. There have been some practical engineering studies on this. They have been able to achieve the sorts of speeds that would be expected for a practical design here on a terrestrial scale. No one's been able to try it out over 30,000 kilometers yet, but we can get to those kind of speeds again with existing technology. There was actually for a while a tether climber competition where they would study both power beaming and gripping mechanisms for climbing up It's a terrestrial one, so they'd string a couple of kilometers of Kevlar from a balloon and run little crawlers up that were being remotely powered by laser. They actually got pretty close to the velocities that we would need for a space elevator system. Obviously, we're talking about a different scale of engineering. Those early studies were looking at much smaller mechanical devices, the size of a hobby drone, basically. But again, this falls under we did it at a smaller scale, and we didn't see anything that said it couldn't be scaled up. So while there is an engineering challenge there, it does seem to be within the realm of conventional materials and conventional design, albeit for a very unconventional application.
Got it. Thank you.
You're very welcome. Which does bring us to the other point. There will be some effect on the tether itself with it moving side to side. While it is in tension, even the stiffest of material over this length will have a fair bit of wobble to it. I don't have a clean answer for you on that. The closest I've got is NASA's been studying tether dynamics in space for about 40 years, and there's a couple of dedicated groups, one in the European Union and one in Canada, that have been actively working on modeling, predicting, and testing those predictions for long length space tethers, and just seeing how various forces imparted on them would affect their behavior. So that's another one. I don't have the answer, but I know there's some smart people working on finding one. And I've seen some of their work. It's actually quite promising.
I have a real quick one. I'm meant to mention the moon tether, and of course, Roy beat me to it. But I do want to know if you have looked into it enough to have determined what the lunar synchronous distance would be.
That's actually a great question. That's one of the weird tricks with the lunar elevator. For a lunar space elevator, you actually end up not wanting to use like a synchronous equivalent orbit. You send the center of mass through, I think it was one of the Lagrange points. It might have been L1, was where most of the designs have looked. So you end up with a tether that's actually much, much longer than the Earth tether. But because of the moon's gravity is so much lower, it can be done with conventional materials. Now, that small one that I was proposing for a heavy lift system to do in one launch would probably only last a few months. It would be a very big science experiment, basically, because as soon as any sort of micrometeoroid or other debris hit it, it would likely be severed. But that's a single mission as a test the idea proof of concept. If it works, you could easily build up a more durable one, something analogous to what we would propose for Earth. Not necessarily the same materials, but the same idea. Build up a more robust tether after proving the concept.
Thank you.
I think Dave is next.
Yeah, I apologize for being out of turn there. I didn't have the participants window. My apologies. Yeah, Mark, just in the same vein, I'm sorry to be a pool of negativity, but it's a fascinating concept. I love it. And thanks, Roy, for your comments about the economics. That was in the back of my mind. It's good you could provide detail. But you look at the present diagram, the lower part of the elevator is going through Leo, which means the good news is it's real thin and a real small cross-section target. The bad news is, oh boy, if you get hit once, bad day.
Yes, that is very much a design consideration. It's actually something I discuss on a later slide. And for what it's worth, don't feel bad about pessimism. While I very much like this idea, at heart, I am an engineer. Any idea presented to me, I start looking for the ways it can go wrong and thinking about what I can do to manage that and if it's possible. When it comes to a space elevator, right now I fall into this is plausible, and I think there's beneficial technology along the way, so it's worth exploring, even if we don't ever get to the goal of actually building one.
Oh, yeah. Can I have a fast follow-up on a different thing?
I'm okay with that, but I also cannot see the attendees list, so I don't know if there's other hands up.
I think I'm the only one for now. Just so I have the mechanics firmly in my mind, which I don't think is true. When I start a car up from the Earth, presumably there needs to be a counterweight that travels the other way from Geo.
Potentially, yes.
Okay, so,
Most likely what we would end up doing is, this is part of the reason we would like a counterweight at the far end of the tether. You can slightly adjust the position out there to balance out the center of mass, either by moving that weight up and down, shifting more weight out there or further back. And you can do something similar with a geosynchronous station. Much of that could be done remotely, so we wouldn't necessarily have to have a human being there doing it. But that is very much a thing that would have to be considered. There will be mass moving around, and we want to keep that balance point very close to geosynchronous orbit.
okay, thanks.
I think
You're
I'm next.
Okay.
So what was just being discussed about being down near LOE? Are we talking about the difficulty of the energy needed to get through that?
That is one thing to consider, but the bigger problem right now is that LEO is a mess. We've treated it as a junkyard for the last 60 years, and there were 2 recent incidents that have caused a major proliferation of debris in that area. One, China decided to show off that they had missiles that could blow up satellites, and so they blew up a defunct satellite, which is a terrible idea. That alone created 10,000 new pieces of debris that represent a hazard to all satellites in activity there. And we also saw, frankly, what we believed would never happen. 2 defunct satellites actually crashed into each other. The odds of that are incredibly low, but it happened. And that too was another massive expansion of debris. Not helping that is the occasional billionaire throwing out a sports car from the window just so they can. So yeah, LEO's a mess. I don't discuss it here, but NASA and the European Space Agency are actively working on some technologies to start trying to clean up low Earth orbit to make sure that we can still get through it safely. Anybody who's seen WALL-E, you may remember that scene where the ship just plows through a bunch of garbage. Cute as that is, that's the scenario we're facing, and it's not something you can just drive your spaceship through. The speeds are such that you would be pulverized.
All right, my second question is, what is the difference between LOE and Lagrange points?
So LEO is an orbit that's fairly close to the Earth. It's strictly speaking doesn't have a definition other than close by, low Earth orbit. Typically, though, it's used to refer to the first couple hundred miles away from the surface of the Earth. The Lagrange points are not something I covered too much here, but if you look at the equations for 3 bodies, the so-called 3-body problem, I've got 3 masses in orbit around each other with
Yes,
respect.
I know the 3-body problem. Go ahead.
Okay. Generally speaking, it cannot be solved. There are a few special cases for which an analytic solution exists. The Lagrange points are one of the first and most commonly used ones. When you have a large difference between the masses of the 3 objects, so object 1 is much, much heavier than object 2, which is much, much heavier than object 3. Object 3 can have a stable orbit with respect to the other 2 objects at 5 specific points. Those are the Lagrange points. They are actually in practical use. I believe Europe has a telescope orbiting one of them right now.
So when you see cannot be solved or hasn't been solved, sometimes there's a proof that they're not solvable.
Yeah, so this one is a lot like the Navier-Stokes equation. There are no analytical solutions that are useful for most practical cases, but you can solve it numerically. So from an engineering perspective, it is a solvable family of equations, and we use it all the time in astronautics.
But I'm asking,
from a mathematical perspective, it is unsolvable.
It's provable that it's unsolvable.
Yes.
Okay, thank you.
Yeah.
Steve
So
M?
we rely a lot on numerical simulation. That's why so many space agencies are at the forefront of computing technology as well. They need it for figuring out these orbits.
Got it. Steve?
Yeah, and we need to let him move on, but I'm going to try and squeeze in one more since we were just talking about the Lagrange points. From the moon, is the whole point to go through the Lagrange point because the moon is tidally locked, and so the Lagrange point is essentially fixed in relation to the moon's turning?
Exactly.
Okay.
That's why.
We should let you get on with your talk, I think.
Okay,
Okay. I do appreciate somebody keeping an eye on the time. As you've probably gathered, I can go on and on about this one for hours, and I am more than happy to. So I do appreciate somebody keeping me moving forward. That said, moving forward. Okay, this is cool, and we've kind of addressed this already, but why exactly do we want this? So, two things. Money. Right now, most of the estimates I've seen put the space market at $400 billion. The next 20 years, it's expected to exceed 1 trillion, and that's assuming no radical changes in the cost of access to space. So none of our grand ideas about rockets getting people happen. Even with that limitation, we still expect this market to double or triple within the next generation, potentially more than that. We're seeing a big expansion of communications. Sensing and observation from orbit is becoming ever more important for a practical basis, weather observations being a very prominent one. We are seeing a lot more R&D that depends on access to space, again, for communications, for simulation, and there's a lot of fundamental science that you just can't do in a deep gravity well. So getting up there is handy. And as we've all seen in the news lately, we're starting to see tourism and even special deliveries coming from both private sector and demand from individuals and governments. So even with no change in technology, we expect space to continue to become more valuable. And if we see advances in technology, there's no reason to believe this wouldn't become a much larger market in a much shorter period of time. Again, I like to think of myself as a bit of a futurist and a bit of a romantic. I'm in this because I think it's really cool and the grand destiny of humanity. But I'm also an engineer, and there is a pile of money to be made for whoever can figure out the technology. And I'm all for getting some of that myself too. The other side is the rocket side of things. Rockets are a bottleneck. The best rocket, the overall rockets are about 1.5% failure rate. Some of them have a much better record, the Saturn V, for example, which I'm showing up there. Failure tends to be unpleasant. Most rocket failures are not, I didn't quite get to the orbit I wanted to. They are, I detonated with the force of hundreds of tons of TNT, destroyed millions of dollars worth of equipment, and probably ended several lives tragically. Rockets are a bit of a hazard. They also tend to be expensive. As mentioned, right now we're looking at $10,000 to $20,000 a kilo to orbit, depending on whose numbers you're looking at. And that doesn't look like it's going to get much better, even if we come up with ways to start reusing rockets and getting more life out of them. Even if we do crack that rocket problem, liftoff is a very violent thing. Every satellite that has ever been put into orbit has had to be engineered for the first 3 minutes of its mission. It is carrying a lot of mass that is useless for the next 20 years, that is necessary to survive that liftoff. That alone is a cost barrier to entry, raising the price of all satellites, raising the difficulty of the engineering design for them, to say nothing of dealing with the hazards of both human and other activities associated with it. And we haven't even left the rocket itself. God forbid we're doing a launch over a populated area, or a rocket goes off course, or some other problem along that vein. Fuel is really the killer here, the tyranny of the rocket equation. I'm not going to go through all of this in detail because we're trying to keep this a little bit light, and I figured I'd spare everyone the calculations, but this one is kind of key. We need a certain change in velocity to get to an orbit. For LEO, that's usually about 10 meters squared per second from surface of the Earth to low Earth orbit. To get there, we will have a rocket with a certain exhaust velocity, Right now, that's around 3 kilometers per second. To get a higher exhaust velocity, you need a much more energetic family of rocket fuels. Currently, our rocket fuels are either kerosene and oxygen or hydrogen and oxygen. You may recognize these as things that tend to burst into flame on contact with each other or with very, very little impetus from the outside, and that tend to have a fairly high energy content. We do know of more energetic chemicals and more energetic materials that have potential for rocket fuel. They cause some problems of their own. Hydrazine is a good example that has been explored and is actually used for rocketry out in space. It's profoundly carcinogenic, and any rocket launch would spread it over 2,000 miles of ocean or land. As you make the fuels more energetic, it also becomes a lot harder to keep them from just exploding rather than combusting. I'm not going to say we are at the limits of technology for rocketry, but it's really hard to leave the Earth's surface. And that really comes down to fundamental physics of how rockets work, not the engineering, not the chemistry advances. You just need a lot of fuel. And that gets worse the further you want to go. Your actual payload to orbit tends to be a lot smaller than the total lift system. Because for every extra pound of payload, I need not only the fuel to lift that extra pound, but the fuel to lift the added fuel, which means I might need a bigger rocket, which will also need more fuel. It is a vicious cycle of design. Going back to our Saturn V here, we're looking at that delta V of 10 kilometers per second to LEO, 30-to-1 fuel to payload. That's pretty much what we saw with the Saturn V. That's pretty much what we see today with SpaceX and with all of the other rockets that are being worked on. It doesn't matter whether the rocket's reusable or not. We have an expensive, dangerous fuel, and we need a lot of it to do a very little bit of work. But this is also why this becomes really interesting. I don't think rockets will ever go away because they're great at imparting delta V to objects. It takes me 10 kilometers per second to get up to LEO. To get to anywhere else in the universe from the surface of the Earth, I need 26.5 kilometers per second. That's a really punishing fuel to payload ratio, 7,000 to 1. But let's imagine I could just carry my rocket up even as far as low Earth orbit. Suddenly, the delta V it had to expend to go 250 miles is enough to take it 250 million miles further. Rockets are awesome. I just want to use them in space. Leaving the surface of the Earth to something that's a little bit less expensive, a little bit more infrastructure oriented. We did talk about this a little bit earlier as well. I'm a bit pessimistic on improvements to rocket technology. I do expect we'll see a lot of things going up in terms of reliability, perhaps even in terms of frequency. I'm just not seeing any places where the engineering can offer us true major paradigm shifts with respect to what we're doing now. Let's say it's $10,000 a kilogram to orbit right now. Maybe we get down to 8,000, maybe 7,000. I don't see any rocket technology going in a way that makes me think we get down to 80 or $8 per kilogram. We're looking at incremental improvements, meaningful, substantial, worth pursuing, as a great deal of money spent around the world shows. But it's not a paradigm shift, and I don't think it will be. Which leads us to what we've also started talking about. If this is such a great idea, why haven't we done it already? And for those who can't see, this is where I'm going to be removing my futurist hat and putting on my engineer one. This is where I start to get a little pessimistic, but also where I start to think that plausible is a good definition for this. Not practical yet, but plausible. So the elephant in the room, tensile strength of our material versus its density. What I've got up here is just the sketch of an Ashby plot where we're showing density on the x-axis, tensile strength on the y. I've got 3 lines drawn across it. The very low level green one is what I call the aramid line. This is anything that's on this line has a specific strength equivalent to Kevlar and other aramids. Put another way, this is something we can already produce in 10,000 kilometer lengths. This is something that is ready to go today. Above that, I have my best case scenario line. For those who aren't familiar, the URI is not a formal unit, but one that's colloquially used within the space elevator community for the relationship between tensile strength in gigapascals and density in grams per cubic centimeter. Named after one of the early pioneers of space elevator research, one Yuri Artsutanov. We're trying to get it formalized, but right now it's an internal convention for this particular industry. It also gives us nice round numbers, which is why I like to use it here. Best case scenario that I see is we get up to 50. Now, 50 is not the best that's ever been seen in theory. 50 is what we get when you take the best measurements we've gotten on carbon nanotubes in the lab, carbon nanotube fibers and bundles, where we've actually done a tensile test on them.
Mark, there's a hand raised.
Oh, sorry, I didn't see that.
Dave?
I'm sorry to hold you up, but really quickly, I'm missing something basic about the plot because things like, Kevlar come at 1 density. I mean, density of the material is fixed, so I don't understand the X plot. Yeah.
Thank you. Apologies, I should be a little clearer on that. We don't really care what the density of the resulting material is. We care that its strength to density ratio will meet certain thresholds. So I said, I know the density of Kevlar, I know the tensile strength of Kevlar. Let's draw a line that goes through that point. And then these other lines are based on similar constraints. Any point on that line would meet that particular specific strength threshold. I'll be putting actual data up on this chart in a moment, showing where a lot of materials fall. Right now, I just want to explain exactly the lines on the graph. So thank you for bringing that up. I should have been a little clearer. So a good way to think about these lines is not referring to a specific material, but as a threshold. When we get to that green line, our material could be used as we might use a Kevlar material in a space color application. We get up to that black line, that's where we're seeing a material that has performance comparable to the best carbon nanotube materials that we've actually made.
Clearer, thanks.
You're very welcome. The plausible line it comes from a very specific thing. I was actually able to get access to a pretty comprehensive database of space launches, and I totaled up the mass of every single payload we have ever put into orbit. A space elevator that weighed that much would require a tensile strength to density ratio on that line. So I'm calling that plausible. It is not practical, but we have in fact put that much material into orbit before. It took our entire history of launching stuff into orbit to get there. So again, not practical. But my definition for plausible tends to be we've done something comparable. And so that's where I've decided to draw that line here. Okay, lines are good, but let's talk about where some materials fall. Roughly speaking, this is conventional materials. Wood and natural products are nowhere near strong enough. This is where I want to call attention to the fact that these axes are log scales. So there's a big distance between some of these numbers that's condensed to fit on the plot. Metals and alloys actually have tensile strengths that are going to be relevant, but they're way too dense. Most steels or titaniums and such are 5 to 10 times the density of water, and water is already really heavy for a space application. So while we can hit the strength, they don't hit the density requirement. Most ceramics have the same problem. They introduce some other issues as well. Polymers alone generally don't get there, though as we have already noted, there are a few exceptions, the aramids being the most common. So again, don't take the blobs I've put on here as representative of every material ever. I have not been able to go through IUPAC's library of 36 million chemicals and plot every single data point for their engineering data. Even if I wanted to, that data set doesn't exist. But these are rough ballparks for where we see most of these families of materials. Composites are where we start to see the exciting trend, where we get above that aramid line, where we're starting to get to the point of high tensile strength materials that have some room for growth and could potentially not work on Earth, but would work on the moon or something similar to that. Okay, so conventional materials aren't going to cut the mustard. Macro scale carbon nanotube threads that we make right now are in that composites realm. They're actually a little higher than that. There's been a paper published since I prepared this chart that pushes that up a little closer to 10 on the tensile strength axis. So still below where we would hope to be or where plausibility kicks in, but we are seeing big improvements there. And I think there's a lot of room to grow. But what we have made, anything that we've made that's big enough to hold in your hand, just isn't there. Stuff that's not big enough to hold in your hand, but that we have made and measured. Small scale bundles of carbon nanotubes, as well as individual carbon nanotubes, have been measured as falling along that upper line. In fact, I defined it in terms of the biggest measurement I could find for a carbon nanotube. It's optimistic. Real materials typically end up maxing out at around 80% of the tensile strength of their molecule once you scale up to an actual engineering object. So we're going to be a little bit lower than that best case scenario line, but it is something that we have in fact observed in the lab. Boron nitride nanotubes are a new entrant into this field with some different properties from electrical and chemical reactivity standpoint. Their tensile strengths right now are a bit lower than what we've seen for carbon nanotubes. Above our plausible line, though still below our best case. As far as practicality, the further we get above that plausible line, the easier this is to launch. Again, at that plausible line, that's the mass of everything we've ever put into orbit, with the possible exception of one very heavy steel plate that we're not sure if we put into orbit or not by accident. That's a story for another time. If you get up to that best case scenario line, your space elevator weighs less than roughly 1 metric ton. You can put that up on a heavy launch vehicle. I don't think we're going to get to the best case scenario line, but we don't have to get too close to it to still see something that really enters the realm of practicality. And while I can't yet make these materials on the scale that would be required, we have made them. This is not theory. These are actual measurements of real materials. So yeah, we don't have the tether yet. Until we get that, the rest of this is a pipe dream. But I don't think the tether material represents unobtainium. It's not some impossible to attain ideal. It's just something that we need to do a bit more research and a lot more engineering and development to bring up from a beaker or benchtop scale into something that's practical for a large engineering object. That's not a fast path. Historically, that sort of development takes 50 years, sometimes longer. So I wouldn't expect to see this happen today without a massive influx of cash. Assuming there's no massive influx of money, we're looking at a couple of generations. But the number crunching I've done in the past for the trajectory of this suggests that at least at the modest scale, something where I can't build a space elevator, but I could build like a bicycle or an aircraft, we should get to a useful tensile strength in about 20 years. 50 years to get both tensile strength and volume of production to the necessary level. So not today, Probably not tomorrow. Probably a while, but not impossible.
You do have another hand up from David.
David, yes.
Yeah, really quick, fascinating, Mark. However, my concern is the maximum tensile strength going to be, you hope that there'll be something like, the relationship with density of, transistors on a chip. But I'm worrying, is the strength of carbon nanotubes and the like reaching up against the fundamental limit of the strength of chemical bonds? I don't know my stuff here, so I hope you can fill out a little bit on that.
Oh, that is a wonderful question. I'm happy to fill out some detail there. That's why I've tried to emphasize the point here about these being practical measurements. Even that best case scenario line, it's based on a tensile test that was done on a small bundle of nanotubes in a modified SEM. So the chemistry can support the kinds of energies we're looking at there at the molecular scale. Scale up represents not only making bigger nanotubes, but also getting them to play nice with each other. We have analogous materials from history, carbon fiber being a prominent one, but a lot of textile fibers are also relevant here. And that's where I'm getting some of these, we expect 80% of the molecule strength in the engineering material from. Might be a little bit more than that, might be a little less, but that's the heuristic from our history with this family of materials.
Yeah, but does that translate into we're not going to do a lot better because carbon-carbon bonds are that strong and no stronger?
So we would be limited there. Like I say, the numbers they used in the Edwards design from a few years ago were somewhere between 60 and 120 gigapascals. I'm predicting, based on what we see in the lab today, that we're going to end up right around 30 gigapascals for that tensile strength of carbon nanotubes, because they're never going to be perfect. I'm an engineer. Perfect doesn't exist. You're just minimizing defects to the level that can be done practically.
So just to make sure I understand what Dave was saying is, so 80 to 120 would in that sense would be the chemical bond strength limit.
Exactly. Yeah. That's
Okay.
the theoretical limit based on the bond strength.
Thank you.
I don't think we're ever going to get there, because as soon as you add a single defect in that bond network, strength drops precipitously. But even when we get down to a manageable level of defects that we're already producing in the lab, we're still looking at something that's 5 or 10 times stronger than any other material we've ever produced. And while it doesn't lead to such a nice, nifty single mission package, it does produce a tether that we are capable of launching. Something that we could put up a very lightweight version of, send very low mass crawlers up, and layer it up to build up a larger tether. It's a more complicated mission. It's a riskier mission, but it's no more complicated or riskier than what we do setting up a suspension bridge, for example.
Mark, I'm going to interrupt you just to let you know it's about 11:20. I will
Oh,
sit
wow.
here and listen to you forever, but I don't know how much more material you have in your presentation.
I am actually getting close to the end, and thank you for
Okay.
bringing that up. I had completely lost track of time. As you can imagine, I like talking about this, and I could go on for ages. So if it's okay with everyone else, I'll go through the next couple of slides quickly, and then we can just shift over to discussion mode. Would that be okay?
We have plenty of time, I think, if you're going to finish up pretty shortly.
Yeah, we
Yeah.
nominally will often go till noon. So if you're getting close to the end, I think we're probably okay.
I am, yeah. So yeah, that's basically the end of this slide. The elephant in the room is the tether. It's the one where we've got some technological limits to overcome, but I have a number of reasons for optimism, both on a research and a practical level. I don't have to rely on theory and perfection to get to the right numbers. I can rely on what I've done in the lab already. In some cases, what I've literally done. As you know, I've done some work with nanotubes myself, so. Okay, but that's not the only issues. There are some environmental challenges. We've got some radiation belts that we'll have to drive through. The tether has to be able to handle those. The crawler and its contents have to be able to handle those. That's why human missions are for a later, much heavier lift system. Keeping a human being safe moving through those radiation belts is something that we've so far only been able to do by going through them as fast as possible. On the slow path, it's just not practical to protect a person. So heavier lift system will be needed to start using people on something like this. As has been pointed out already, Earth's atmosphere does represent a hazard. Oxygen and ozone are pretty reactive. We have very exciting weather down here, and global warming is making that even more exciting as time goes on. We've already talked about space debris. It's bad in LEO, but it's relevant everywhere. We have seen some designs, even going back to the proposals from the 90s, that mitigate the effect of a single impact, but it will be necessary to be able to repair damage on orbit without having the tether come apart. So a challenge, to be sure. Crawler design itself, we've already recognized this is going to be some pretty high-tech mechanical engineering. Not unachievable, but definitely top end of what we do. Launch and deployment is a challenge. Our base station would probably be a ship to give us some mobility to protect the lower end of the tether, but now we need to have a mobile station, similar to the way a lot of oil rigs function. How do we build up the ribbon from the initial mass deployed at launch to the final mass for the functional device? We've had some promising things for power beaming, but power beaming ultimately is pointing a pretty potent laser up. Or if you're power beaming from Geosync, pointing a pretty powerful laser down. Both have their challenges. And weather monitoring, of course, will become important because we need to avoid as much as possible stormy weather on the surface. And that's before we get into all of the usual terrestrial challenges. We're not talking $1 trillion project, but this would easily be in the billions, tens of billions. Financing is an issue. How do you manage something like this? It crosses international zones, it crosses national zones. You've got questions about ownership, about whether it's infrastructure or a specific technology project. As has already been pointed out, it also interferes with lower orbits, so that's something that has to be negotiated and planned for, which brings in politics and brings in law. Law is actually really complicated here because part of the reason we want to put this at the base station out in the ocean is so that at least the whole thing is covered by the law of the sea, which leaves lots and lots of gray area. And security, as has been pointed out. Thankfully, if this gets damaged or gets intentionally damaged, we're not looking at a catastrophe, but it's still something to be aware of, as you would have to be for any large-scale piece of infrastructure. And so to end with a few thoughts on why I think we should keep looking at this. It's ambitious. It's not currently practical, but it is within the realm of plausibility. Similar projects on other nearby bodies in space are actually currently possible. We can do the moon now, and Mars is not that far outside of what we can already do. Both have their own unique challenges, but would be very good stepping stones to a bigger project like this. And as you probably noticed with a lot of those challenges I mentioned, there's a lot of value to be drawn from them, even if this project fails. Power beaming is something we're already looking at for future space missions. So you can have a high power generation at a base station, which is then remotely beamed to a fleet of rovers. We're also looking at for exploration on the Earth. It's a great way of moving through open terrain, like in the Arctic or in other areas where it's difficult to have mobile power, but you need a lot of mobility to adequately explore or patrol the region. The advances in weather monitoring that we would need would have practical benefits for every person living on Earth right now. Better weather predictions, less hazards because we're able to plan in advance. High-strength materials are valuable in their own right. Even if we never get to the tensile strength for an Earth elevator, something 10 times stronger than what we can make today in scale is going to have a radical impact on our materials technology. So even if it fails, there's a lot of exciting, valuable technological and practical contributions to the human endeavor that would come out of this. And if we succeed, even the short-term becomes a paradigm shift for space access. Long term, going to space costs as much as going first class to your favorite international city. No longer is the playground of the ultra rich. It's something we do for a honeymoon or for a special trip at one point in our lives, which makes it easily accessible for business and economic activity and the exploration and exploitation of all of those resources. And the obvious, space is awesome. It's cool. It has captured the human imagination since before we could write, since before we had words. We looked up at the sky in wonder. An image like this used to be the common heritage of humankind. Most of us can't see this anymore because of light pollution, but this is what's inspired us for 10,000 years. And everything we've learned taking our first tentative steps out there has made us want to go further, has made us want to do more, has made us see the value of what can be done when we work together to reach that. And even if we can't, I think the benefits that we would get just from the new perspective on home are very, very valuable. And so for my final slide, I'm not going to bother trying to say this myself because it's already been said better by one Mr. Carl Sagan. You may have seen this picture before, the pale blue dot. This is a picture from one of the Voyager probes looking back, and I've taken the liberty of circling the dot in question in red. And to borrow from Mr. Sagan, look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every saint and every sinner in the history of our species has lived there, on a mote of dust, suspended in a sunbeam. Like I said in my last presentation, small things working together can lead to big things.
I think that's a
When we
good
build big
definition of
things-
claustrophobic.
Yeah. When we build big things, we can get that unique perspective. And even if you and I never join Voyager out there in the stars, I think the benefits for those of us who stay here at home could still be tremendous. A real improvement in quality of life and something big and grand to look forward to look out to. That's all I've got. Again, thank you all for listening. I'm happy to keep talking. Obviously, this is something I'm very fond of, but I appreciate the opportunity to share that with you.
Thank you. That
Dave
was
is
good.
next and Bernie is after that. Go ahead. Dave. Unmute, Dave.
Okay. Mark, may I just say that you and Carl are poetic in the best sense of the word. Thank you very much for that. But
You
also,
are very welcome, and thank you. I very much appreciate hearing that.
also just a minor thing, since I've been so negative, I will now be thunderingly positive. One advantage I see, which I think you kind of covered under cost, is that if we are going into space, it seems to me that this is energetically very efficient. That is, that in energy as well as dollars. So
Very much so. Most of the proposals right now would look at power beaming from Earth up to the crawler. You'd be looking at basically pointing a laser at some large PV cells on the crawler itself. That can be a very efficient energy conversion. And even if it's not, we're talking about using electrical energy from a power grid. In terms of the actual cost of the energy required to change potential energy through that orbit, it's $5 a pound less. The cost the cost of our fuel becomes incredibly low because we're using electricity. And if
carbon
we can
cost goes way down, yeah.
Yeah, and if we can find the political and legal will and structure to get power generation on orbit and have some of those lasers pointing down, the efficiency only goes up from there. And there's been a lot of proposals for space-based solar power just because of the increased efficiency as well as the increased exposure time. It's not practical yet because it's just too expensive to move that much mass from the surface of the Earth up into space. But that's why this sort of design very much appeals to me. What we've talked about today is really a first step. This is, let's build a space elevator to work with the market that already exists and that we expect to see grow in the next 10 to 15 years. Once you prove that the first one is possible, once you do the first one, it's really easy to make a second one or a third one. And it's really easy to make the next ones a lot bigger than the first one. So suddenly a lot of these pie in the sky applications become fairly practical, fairly cost effective, to say nothing of the environmental benefit of implementing solar power for the whole world.
I want to interject one real quick thing. If you turn off your view sharing or your screen sharing, you will probably be able to see the matrix of participants, and then you'll be able to see the hands up, I think.
Yes, that is. Oh, yes, I can see some hands now. Thank you.
Okay. Now, my question relates to the energy requirements. If you're strictly going up with a rocket, yes, you have to also account for the weight of the fuel, and that's the biggest use of the energy. When you're on a tether, though, traveling upward, you're still just moving radially out from the center of the Earth, fighting gravity directly. You're not taking advantage of airfoil lift or anything like that.
Right.
So I'm not sure why you couldn't do the same thing without the tether. The tether's just a guide to keep you going straight. Whereas if you use those beams to lift anybody without the tether in there, wouldn't it be roughly the same energy requirement?
It would be. And in fact, there has been some exploration of using high energy pulsed lasers at a very reflective surface on a satellite or other object to get it to achieve liftoff. Those experiments have shown some exciting promise. We've managed to lift a couple of kilogram objects up to 0.5 kilometer or so.
Yeah.
So like the space elevator, it's a fairly nascent technology. The limit there largely comes in because of the very high energy that those lasers need. With the space elevator lasers, we're talking about a modest power over a long period of time. The ones without the tether require very high energy pulses happening very frequently, which has proven to be a little bit more difficult to do from a lasing perspective. Certainly possible. And I grant they're both at about the same stage of technological development. So talk to me again in 5 years, I may well have changed my mind.
Okay.
But right now, what I'm seeing is that despite the material challenges, the other engineering for the space elevator is a bit simpler than some of the other approaches that would just use either directed laser power from the surface, or the example we're often familiar with from when we're already in space is solar sails, relying on photon impingement from the sun itself for our motive power. Again, there's evidence of both of these being effective. To be blunt, it's just not what I wanted to talk about today, but other options exist, and that's definitely a good one.
Steve,
A good point to raise.
Steve, your turn.
Yeah, so that last question confused me and kind of goes back to my first question, and then I have the original question I was going to ask. So is this car climbing the rope? Is it using pulling on the table, or is it just a guide? What is the mechanism that's getting this thing to move?
Yeah, so the mechanism here for the design we've presented, the cable is both guide and trackway. So you could probably, actually, can you all see me right now?
Yeah.
Okay, so I'm going to do a very quick jury-rigged example here. Let's say my phone here is the cable. My crawler is going to have wheels engaged with it on either side and use that to roll along up. I'm going to beam power down from the Earth to drive those motors. But essentially, we're looking at a mechanism similar to, say, a monorail or the types of rollers you might use in the printing industry for sending paper through a printing press.
Okay,
So
so
similar in mechanism there.
that's
Other
what I
approaches we were just discussing don't use the tether, and so they have some other challenges. We like the tether for some as a solution to some of those challenges, while it does introduce other issues.
Okay, so that's what I had understood you to say earlier, was it's climbing up the rope via rollers. But you're
Exactly.
saying there are other approaches that may simply use the wire as a guide.
Right, or may not use it at all.
Okay, okay.
Those are being studied. In my personal opinion, they are not as far along and don't show as much promise for the near term. But in all cases, we are talking about somewhat speculative science. It's near term, it's not science fiction, but it's also not reality yet. So this is very much the kind of thing that somebody having that serendipitous accident in the lab, or some industry finally cracking the code on their catalyst or production process, could have a big impact on which one of these is more practical.
Okay. Bernie, if your question is still on that topic, go ahead, and then I do have a
Yes.
different question.
Okay. Well, you just mentioned that there would be rollers on either side of the cable, and
Mhm.
they would then start to walk along it. But as soon as you put any kind of force into that, aren't you changing the whole gravity dynamic that's keeping the end of the tether up at geosynchronous? You're suddenly introducing more gravity in a way, or it feels like gravity to the system.
There is definitely a force balance that has to be accommodated. This is part of the reason, I didn't go into this in too much detail, but this is one of the reasons that most designs incorporate some sort of an active counterweight at the far end of the tether. Most likely that would be made of some of the crawlers used initially to bulk up the tether from the first seed that's dropped down up to its final mass. You could then have those be able to come in or come out, reeling in a little bit, changing the mass balance on the other end so that the change introduced by the crawler coming up still leaves us with a nice balance at geosync. There is some work to be done, but this is, oddly enough, this is actually one area where the vast scale of the object is to an advantage for us. It means that these forces propagate relatively slowly along the whole length. So it's fairly easy to develop a control loop to balance that mass. There are some other forces that are a little bit trickier, and this is where some of that tether dynamics stuff comes in. That I think I mentioned the group in Canada that's working on that. If you have a cable this long, there will be oscillation. There will be overlapping waveforms, and those will need to be managed and controlled. Their early work suggests it's possible, but their early work is mostly based on tether experiments done over the last 40 years, dealing with tethers on the order of a few hundred meters. So there's some question about whether it scales up to this full size. That's another one of those areas where the science we have is very promising, but the scale does raise questions that we haven't had to address yet.
I think I'm next.
Well, actually,
yeah.
Gary, I did have my other original question, if I could go ahead and do that one.
Yeah, Steve, whoever's on the left top corner of the matrix is the next one to have raised their hand.
That does seem to be true. It seems to be
Yes.
putting people up in line in a sense. Yeah,
Yes,
I
it is.
originally had a different question, and then Bernie's question kind of got us on that conversation. My original question was, so I'm thinking about how the thing's initiated to begin with.
Mhm.
So you start at geosynchronous orbit, and you're feeding this cable up and down, I guess. Does it go up in coils, and then you kind of let it out? Is it extruded from there? What is the process itself kind of look like to build it initially and build it up, as you've been saying?
Yeah, that's a great question. Again, for time reasons, I left it out of the talk itself since we're trying to be a little high level, but that is something that we've explored. The current idea, since we expect the final mass of this initial tether to be more than can go up in a single launch, we do an initial launch of a cable that has the appropriate length, but doesn't have that 20-ton capacity. It probably has a capacity on the order of a few hundred pounds, maybe less. We take that to GeoSync. We deploy it in either direction from there, bringing one end to the Earth and one end out into that farther orbit, giving us an initial seed mass out there as well to, again, help us start balancing these forces. This is actually the most dangerous part of this mission because this initial seed tether is going to be very fragile. So a stray micrometeor could be a problem here. So we need to build it up from there fairly quickly.
How do
So
you
once
catch it in the wind on the Earth side?
That's one of the questions. Freely admit that's an open one.
That's a good
Current
one.
designs suggest using either a small airfoil or small rocket for the last few miles to get to the surface to give us some control. We're still speculative there. That's one of the ones where we know it can be done, and since it's not an immediately limiting factor, most of the design effort has just said somebody else can worry about that in 5 years. It's doable. I don't want to do it now. But it is a real thing. It is a factor to be considered. So once that seed tether is laid out, though, then you would start sending these lighter weight crawlers up. But instead of carrying a payload for a mission, what they carry is more tether material. And you layer it over that initial seed tether. And you send up more and more of these missions until you build up to your target capacity with whatever its safety factor is. This is also very similar to what you would need to do to repair damage along sections of the tether anyways. So its technology will want to develop for the project. It does mean that that initial launch and that initial seed is a very risky moment for this project. If it fails, we're going to have to do a new seed launch. That's expensive. After we get that initial seed tether going, it starts to become safer and more stable. And truth be told, the first payload you lift after you build a space elevator is your second space elevator. You have that coiled up and ready to go on the ground. And as soon as you get to target mass, that goes up. So now I have two. So if one fails, I still have a way up. And I can use that as a way back down. So my crawlers become reusable. I just have this constant loop going up and down every day. Gets a bit more into the logistics and some of the nuance. There's some other proposals for how to do that deployment and how to schedule lift and retrieval. Again, that's been treated largely as a logistics concern, where the right decision is going to depend on the detailed design as we get closer to deployment and on what we end up with as our practical liftoff and launch schedule. For all we know, when people see this start to go up, they say, all right, it's time to get in on that cheap satellite game. And we see the market double, not in 20 years, but in 10 years or 5.
Mhm.
So there will have to be some adaptation, both during the deployment and initial first few years here. And as I said, I don't expect to displace rockets completely initially. For people, at least, we'll still need them to get up there. But for a lot of material, for a lot of satellites, there's significant design advantages. And as this starts to become a regular thing, we start to see more traffic. We justify heavier lift elevators, eventually getting us to where people can go up on them. And then we can use rockets for space travel out in deep space. Not the hard work of going 100 miles up, but the hard work of going 100 million miles away.
Gary's got one.
Oh, yes, Gary, sorry.
Yeah, so, how far off the Earth is weather a problem? Where does it stop? Now, I assume at LOE, there's no weather, there's no wind.
More or less, no. So when usually we say about 10 miles up or so is where weather stops becoming a thing. That's an approximation. There is still atmospheric movement above that. And in fact, that is still a significant contributor to drag. The International Space Station does periodically need to have energy imparted to it because there's enough drag even 250 miles up that it is slowly losing orbit. So there will still be atmospheric forces at play several hundred miles up, but they become less significant.
All
The
right.
International Space Station doesn't have to have a constant energy input to stay there. Just every year or two, they have to have a couple of retro rockets fire to bump them back up.
So you mentioned that you have to worry about weather. Now, when you have a tether, it's stuck at the base.
Yeah.
How do you adjust that for bad weather?
That's one of the reasons we'd like to deploy this both in the Pacific Ocean off of South America, because the weather there is very, very boring, even with our exciting global warming, changing weather stuff. And because having the base be on a ship or oil platform type thing means we can move it. We can only move slowly, so we have to have good weather prediction. We need at least 2 days, not 2 hours. So that would itself be an advance over what we currently do. But again, it's not a radical change. It's an advancement that we're already working on and that would have benefits elsewhere. So the ship would be able to move around a little bit around the equator. It doesn't have to be exactly on that line. If we're a little bit north or a little bit south, the payload limit drops a little bit, but easily accommodated for by the kind of safety factor you'd want to build in anyways. So a mobile base station has some challenges, but it's actually not an unusual technology. The vast majority of rigs in the Gulf of Mexico, for example, are mobile. They go from oil well to oil well, pumping and drilling as needed.
Of course, they don't have an infinite pole on top
Yeah.
of them, right?
Yeah, they don't have a giant tether hanging out the top, but the mass of the tether would be less than the mass of a ship. So there's actually not that much in the way of kinetic energy to be worried about there, or potential for having to start and stop. We really are more concerned about just making sure there's not much in the way of lightning strikes or other storms around our base station.
So now you got your tether built and it's working wonderfully. What about its vulnerability to bad actors or meteors or weather? What if it breaks? Is the whole project shot?
Well, this is why the first thing I do after I build one is build a second one,
Now, is
because
the second one very close or far away?
you'd probably do a little further away just to make sure that no oscillations on orbit would be a big issue. Maybe you'd go a few hundred miles further out into the ocean, or maybe you'd set one up off of one of the coasts of Africa. There are similar but not quite as good quiet weather zones there.
But how do you move it? Oh, I guess once it's set up from the first one and it's on a ship, then you could move it.
Right, and that's the thing.
idea.
Changing position in geosynchronous orbit, you would deploy from a different location, and so your base station would be different.
Got
But
it.
that's where this gets kind of weird to think about. Because of the sheer length that we're talking about, when my base station moves 10 or 20 miles, most of the tether basically stays where it is. We
Right.
really are just dodging weather in the last 1/10%
I
of
got
the
it.
length of this object.
So does this tether curl a little bit? It's not a straight thing.
You'll
got-
end up having some waves and vibrations moving up and down the tether. Because of the high stiffness of the material, they'll tend to be low amplitude as a percentage of length, high amplitude in an absolute sense, just because of the sheer size of the thing. This is why modeling how these vibrations are going to move up and down the tether is going to be important, because we can actually use this to our advantage. One, we can do some active dampening. Again, we have some ways of controlling mass and position of mass. So we have some controls over how these vibrations will go. And since we have some control, we mentioned that there's going to be satellites in low Earth orbit that we're going to need to avoid. Instead of having to worry about sweeping out an entire orbit and saying nothing else goes here, we just make sure when we move through this section of orbit, we're having that part of the waveform going around the satellite.
So how far will the top of the two tethers be from each other? Will
Uh,
they be the same point or will they move off a little bit?
oh, they'd be quite far apart from each other.
would be.
We're probably talking a radial change on the order of several degrees. The absolute distance at the far end would be tremendous.
No, I'm talking about the close end, up in the.
Oh, the
orbit.
close end, we'd still probably keep them at least a few hundred miles apart. If you're going to build two, you may as well put them on opposite sides of the world for easy access from everybody, as well as keeping them as far apart as possible. There's some arguments for putting up 3 or 4, again, roughly equally spaced, both for ease of access and for there's some potential telecommunications benefits. You'd basically have global coverage and global observation from the 4 geosync stations at that point. And since it's easy to lift mass up to there, you could build out some pretty valuable communication and observation infrastructure.
Okay.
That's
now-
actually, that one I'm stealing from Arthur C. Clarke. He not only wrote several books about that, but got a patent for it. But it's also something we do today pretty commonly. So,
All right, now back to the chemical
Wait,
bonding.
Gary, you just had 4 questions.
Yes,
Can we
but you
give?
had many more than I had throughout the hour.
Oh my God.
So let me get another one in, okay? May I please?
Go ahead.
Okay, and I thought I was in the upper left-hand corner and you're fourth. Okay, all right,
Yeah,
here
but
we
there's
go.
3 people behind you, Gary, and we've only got 9 more minutes.
All right,
So
I'll
just
shut
make
up.
it quick.
I'll shut up. Dave, you're next.
Okay, Mark, I'm really fascinated by the dynamics of the cable, which sound like they could be very important. So very quickly, you might have to have damping masses that travel relatively independent of the cars. That might be a
right.
little bit tricky. I'd love to hear more about that, but the question really is, I was fascinated by your description of how you deploy the thing initially from geosynchronous orbit. You have this very thin fiber that you have to make sure follows the right path.
Right.
I'm just wondered, how thick do you envision these fibers being? Because you have to design crawlers that don't mind, traveling along a thread. And for some
Right.
reason, it strikes me as a good trick.
Yeah, the initial ones, we would probably exaggerate the profile at the expense of thickness. So we'd end up with something basically like onion skin paper, maybe even thinner. We'd be relying on the high inherent strength of the material, as well as some abrasion resistance, which will have to be designed in to handle those lighter weight crawlers, because you'd need some surface area for contact.
Yeah.
Crawling up a thread is much, much harder than crawling up a sheet. And this is where the engineering side of things kicks in, and where we have to say we don't know enough to know for sure. We've got a pretty good idea of what kinds of friction we could tolerate, what kinds of friction and resistance will be required for a device. But the question is, how close can we get that in a single mission, in a single launch profile?
Yeah.
Maybe we have to launch 2 or 3 initial payloads, splice together those cables on orbit, and deploy that first. The design studies we've worked on so far focus on trying to make that first mission a single heavy launch, entirely for cost reasons. If necessary, you can do potentially a multi-launch scenario and splice together that thicker fiber for your seed cable.
Yeah.
It just adds a lot more expense. So if at all possible, we want to avoid it. And so typically we stipulate that we've avoided it as one of our design constraints. But I'm the first to admit that that is an assumption we are making, not a guarantee we can offer.
Okay.
So it would potentially affect the initial capital cost of the infrastructure.
Thanks.
Steve, you're
Of course.
next.
Yeah, so I'm trying to imagine traffic control. Is
Yes.
there like the way we're describing the mechanism, it seems like there can only be one car going up or down, in which case, is there some way of getting multiple cars on a line? Or do you have
Yeah.
to have multiple lines and then they have to be spread apart? And part of this question was also, I really am curious, how much wiggle is there in miles? You were talking about avoiding storm cells on the ocean? There's that much of much room to move around. How do you manage the traffic going up and down and keep the cars or the wires from hitting each other all the time?
Well, let's start with a traffic question, because that's one we haven't touched upon yet today. And it's one I think is really important. If we have a single cable, we can only go up or down. So most likely, if we have a single cable, we're always going up. Each crawler carries with it some useful payload and then either joins our counterweight mass or joins the station at Geosync to be used for whatever the next project is. If we have 2, one of them goes up, one of them comes down. And you just do a little orbit shift to move from one station to the other when you want your cable to come back down. Both have some advantages. Just going up leads to some waste and cost issues. Coming back down means my system requires 2 elevators before I'm doing all that much, which introduces some challenges. But there have been logistical schemes for going both up and down on either a single tether or multiple tethers. Conveniently, we can have multiple crawlers on the tether at once. As we move up through Earth's gravity well, the addition to the tension on the cable from each crawler becomes less and less from a mass basis and just becomes from that friction of the rotating rollers. So again, for our early design cases we've got, it's usually worked out to be, we have one launch a day and it takes a week to get to geosync. So there's 6 or 7 crawlers on there at any given time. Mostly that's done from a throughput perspective. There's no reason it has to be that way. That's just the logistical approach that has generally been settled on. There's nothing that says we couldn't just do a couple of bigger launches and then do that for a month and then have 2 weeks where they all come back down. There's other possible schemes here.
Okay, that answers the question then. Thank you.
You're next.
I wanted to ask about the debris in low Earth orbit. Now, it's my impression low Earth orbit starts somewhere around 60 miles. And as you said, the space station is 250 up, so it's at least that. I don't know how much further it goes beyond that. But,
It's bad the whole length.
Okay.
All of Earth's orbit between Leo and Geo is a mess. It's worst at Leo because that's where most of our stuff is, but
Yeah.
it's bad all over.
But now, the satellites that we're putting up for communication, and any satellite that's put up in low Earth orbit does not have to have an equatorial orbit like geosynchronous does.
Right.
So, in other words,
it
it could actually be going pole to pole.
Yep.
I'm not sure that the concern about the debris or the other satellites in Leo is really that bad. I mean, that's a vast envelope of space.
Yeah. Other satellites, I'm not too worried about. Even if we see a tenfold increase in what we've got up there now, it still doesn't represent a significant problem. It is one we anticipate becoming a problem, though. CubeSats are already becoming very, very popular. For those unfamiliar, they're very small satellites that you would typically launch in large fleets from a single lift vehicle. You would end up with swarms of hundreds or even thousands of these tiny satellites. That's really popular today and expected to grow substantially in the next 10 years. So we expect Leo debris is going to grow proportionally, if not exponentially, just from that. So while debris right now is manageable, we see impacts frequently enough that we worry about it, but not so frequently that it's a go, no-go condition for the design. We know it's going to get worse. As I mentioned, NASA and the European Space Agency, they're already working on various proposals for ways of deorbiting some of the larger, more threatening debris to go up and basically clean up Leo. Rather amusingly, one of the gentlemen working on that, Jerome Peterson, is the guy who did the space elevator work at NASA back in the 60s and 70s. So I've gotten to see him speak a few times. His passion these days is on making sure we can keep getting to space through all the garbage in Leo. But yeah, it's not a problem today, but we expect it will be tomorrow. And so it's one we want to account for now so that it doesn't surprise us at the worst moment.
David?
Yeah, just tacking on to that, Mark, I always get a huge charge out of people's designs for cleaning up Leo debris, and I cheer that on because if we can't get through Leo, we are really screwed. But
yes, it's hard enough to leave the Earth's surface already.
The question I have, though, I'm sorry, it goes back a little bit to materials because, I mean, your mention of the radiation belts brought something to mind. Yeah. We require that the material have a very, very high tensile strength. And nanotubes are great, but do we know how they stand up to radiation?
We do. Carbon nanotubes do okay with most forms of radiation. It is capable of breaking that bonds. So any alpha or beta particles coming in through are going to be a bit of an issue. Conveniently, carbon nanotubes are known to have a self-healing mechanism at high temperature.
Really?
So one of the proposals we've looked at is every 6 weeks, one of the crawlers you send up doesn't have a payload. It's got basically a set of ovens in its roller, and you heat treat the whole thing to get back its strength. One of the other things we've looked at, and this is why I left boron nitride nanotubes on that chart, They're probably not what we'd use for the main reinforcing phase, but they're a really durable ceramic. They eat radiation for breakfast like nobody's business, and they can handle a lot of the electrical discharges we might see at lower atmospheres. They're also not very reactive chemically, which is very handy since carbon has no stable oxide. It turns into a nice gas and floats away. So we aren't quite there yet, but our current speculation is that the main tether will be a load-bearing capacity of carbon nanotubes jacketed with a thin layer of boron nitride that won't compromise strength too much, but will offer practical benefits from a materials perspective for ensuring longevity. Somewhat
Very
speculative at this
cool.
point. Like I say, every one of these is something we've shown in the lab, but we've never shown them all on the same object at once. So
Very cool. I must say, I love the mobile annealer for some reason.
yeah, exactly.
Really, one thing in common, and then I'll be quiet, is your offhand remark about the steel plate. Was that the thing from the underground nuclear explosion? Yeah,
Yes,
yeah.
exactly. For those who aren't familiar with the story, there was an underground nuclear explosion plugged with a very large steel plate. We have exactly one frame of film showing this steel plate moving upwards at what might have been escape velocity. So it's possible one of the first large objects we put into space was a nuclear bullet. We're not sure. It may have just vaporized or something, but yeah, that's our big errant object up there.
I've just got a quick one. You were talking about moving the base to accommodate bad weather. Wouldn't all the movement have to be equatorial, though? You couldn't move off of the equator because then you're changing the dynamics again.
So, strictly speaking, you're correct. We want to stay close to the equator. If you deviate from the equator, the big problem is that because of that extra angle, the tangential force there, your load-bearing capacity drops down a little bit. So this is one thing we'd need to accommodate in a safety factor for the elevator strength during design. We know we'd need to go off equator a little bit. We can keep the balance at geosync with that counterweight mass, but we need to make sure we have sufficient additional strength built in to handle that movement.
But you've suggested that there's miles of tolerance there.
Yeah, there is.
Wow.
That's where this gets weird. Even if we're using carbon nanotubes, which are one of the stiffest materials we know and don't have much in the way of elongation, it's kind of like optical fibers. Glass generally doesn't like to bend, but you make it small enough and you can get a pretty tight bend. This is the other end of that extreme. Nanotubes don't like to stretch much, but when I started with 100,000 kilometers of them, it's not hard to find 10 or 20 or even 100 kilometers of give. Again, the details need to be worked out. That's a common engineering problem, but that's also why we're not too worried. That kind of safety factor, that kind of accommodating for tension changes is something we've been doing as a species for centuries now. It's well within our existing capabilities. This is just a little bit bigger than what we've done before. Looks like Roy had to go.
So I'm not used to having art meetings. It's been a while. Without lunch afterwards, are we now all going to go get our sandwiches and bring them back and have a little lunch discussion?
I'll leave that up to the group here. I can spare a little bit of time if we wanted to keep talking. It's a little early for lunch for me, but I'm okay with that.
Yeah.
But if everybody's got plans and we need to go our separate ways, that's fine too.
And I was actually just kidding, so that's not necessary.
Okay.
Gary, did you have another question?
I do have that question I wanted to ask. Roy left, but it was in relationship to your discussion with him about chemical bonding limits.
Mm-hmm.
Is the chemical bond a fixed limit, or does it depend on the atom?
It's going to depend on the atoms in the molecule. We know the bonds for carbon nanotubes and boron nitrides pretty well. As we talked a little bit in my last presentation, nanotubes are pretty much delocalized bonds across the whole structure. So you've got a nice uniform strength within the tube. There are some concerns about transmission of load among tubes. That's one of the reasons we haven't seen these high strengths outside of the lab yet, because there's still some practical development to be done there. Boron nitride is similar. We understand that bond pretty well. But our limitation here ends up not being so much the bond strength as the number of defects. No nanotube will ever be perfect. There will be a missing atom here. There will be an extra hydrogen that we didn't quite remove over there. Those defects both change the way load is distributed within the structure and are often higher energy, which means easier to break than the other bonds. So that's where a lot of my plausible line and why I say we'll never achieve the optimistic one. You'll never completely remove defects. We can get really low. Silicon technology has shown you can get really low with those, but they never go to zero. And we're going to be in an environment that will add more during the life of this system. So our real limit.
What about changing the atom?
We could try using different materials. There are other stronger bonds, but none has really shown practical application for large scale production in a tension environment. That's not to say it doesn't exist, but we haven't found it yet. And so
Okay.
we've confined our work thus far to materials we know exist and that we know we can make in at least some quantity.
Got it.
But
Thank you.
like I say, there's plenty of room here for a magic bullet. Somebody could have that happy day in the lab and change the whole equation for us.
Got it. Thank you.
You're welcome.
Well, anybody else have anything to say except thank you very much for a great lecture?
I want to say thank you very, 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 very much. Like the
You
last one,
are-
this was fascinating to me, and I think you hit the level of conceptual difficulty, the complication level. I think you did a good job hitting this group this time. You went into enough detail that it really challenged people, but it was still quite comprehensible. So
Good, I'm glad.
very, very well done and very much appreciated on my part.
Thank you for saying that. And you are all very welcome. You're a great group to talk to, and I really enjoy having the chance to do so.
So when can you come back again?
Well, that's a good question. I got to come up with another topic first, but once I have that, I'll reach out. We'll get me on the calendar.
Let us know.
That'd be
This is
lovely.
your obsessions and we'll talk.
Yes.
Yes, I may well do that.
Okay, I'm signing off.
All
Sounds
right, I
good.
will stop
Goodbye,
the
all. Thank you
recording.
again.
Thank you very much, y'all.
Okay,
Bye-bye.
bye-bye.